We map physical reality using three familiar axes: length, width, and depth. Moving an object through that space requires exactly 6 degrees of freedom. You have 3 directions for translation along the axes and 3 planes for rotation. But trying to chart all 6 of those independent variables simultaneously on a standard 3D grid quickly creates a tangled, unreadable mess of overlapping vectors. Our standard 3-dimensional container is simply too constrained to map out those complex mechanical motions as a single unified mathematical object. To solve this, mathematicians insert 3 entirely new axes, perfectly orthogonal to the first 3, intersecting at the exact same central origin. This creates 6-dimensional Euclidean space. Every single location in this arena is pinned down by a 6-number coordinate, while retaining all the standard rules of linear vector math. By expanding the geometric arena, a chaotic 6-variable problem in our world stretches out into a single, precisely plotted point in a higher dimension. This higher dimensional arena is mathematically strict, operating within exactly measurable bounds. The most straightforward boundary is the 5-sphere. This is a 5-dimensional surface where every single point sits at the exact same distance from the 6-dimensional origin. Look at this equation for the physical volume trapped inside that boundary. The volume, V6, equals pi cubed multiplied by the radius to the 6th power, all divided by 6. That evaluates to approximately 5.16 times the radius to the 6th. Because of how rapidly higher dimensions scale, this sphere fills a surprisingly tiny fraction of the space around it, occupying barely 8% of the smallest 6 cube you could fit it inside. The ability to calculate these exact volumetric limits proves this geometry operates entirely on firm mathematical laws, rather than theoretical guesswork. Inside those curved boundaries, we find the internal architecture of 6-dimensional space, the 6 polytopes. You can construct infinite shapes here, but strict geometry dictates that only 3 perfectly regular shapes exist in 6 dimensions. This diagram shows the 6 simplex, the absolute simplest of these regular forms, requiring the minimum number of coordinates to construct. Moving down the table to the B6 family, we find the remaining 2 regular shapes, the 6 cube and the densely interconnected web of the 6 orthoplex. Those 3 regular structures serve as the foundation for a much wider family of complex, uniform 6 polytopes. Notice the distinct rings below each shape. These are Coxeter-Dinkin diagrams, identifying the specific mathematical domains of reflection used to build each uniform geometry. When mathematicians shift that symmetry group to the D6 family, the structure alters, generating the 6-stemic cube, missing exactly half the vertices of a standard 6 cube. Finally, the E6 family pushes complexity to its absolute limit, resulting in the intensely overlapping 2-2-1 and 1-2-2 polytopes. These symmetrical matrices require spatial coordinates and structural alignments that simply cannot physically exist under standard 3-dimensional constraints. So, if these architectures exist strictly in a mathematical void, do they actually touch observable reality? It ties back to the 6 mutually orthogonal axes that built the original coordinate system. The angles and relationships between those 6 axes perfectly match the primary symmetry axes of a standard 20-sided 3D icosahedron. Because the alignments match, mathematicians can execute a projection, essentially shining a light through a 6-dimensional shape to cast its 3-dimensional shadow into our world. Crystallographers rely heavily on this exact icosahedrally symmetric projection to solve complex molecular problems. When studying icosahedral quasicrystals, this higher dimensional projection provides the literal blueprint required to map out their seemingly chaotic atomic bonds. We establish a purely abstract coordinate system and find it acts as the exact architectural engine, predicting the atomic structures we hold in our hands.